In section 2.3, we're going to look at deductive reasoning, which is using facts, definitions, and accepted properties in order to write a logical argument. So instead of using patterns, we're going to be using direct evidence, okay, instead of the circumstantial evidence we use to build a conjecture in inductive reasoning. Deductive reasoning is going to be the basis on which we build proofs later on. First, we have to look at two rules of logic. The first one we're going to talk about today is the law of detachment. So if I have a true conditional statement in the form of if P then Q, and P is true, then logic, as well as a little common sense, says that Q is also true. So what that looks like in words is that if I have a true statement and I am given that P is true, I can conclude, therefore, that Q is true. All right? And so in symbology, on the left, we have our statement, our given, and this symbol also means therefore Q. This makes a little more sense when we actually look at it in terms of using it. So we're going to use this law to make a valid conclusion. So if I have a true statement, I can make a valid conclusion from it. So first, let's identify P, the hypothesis of our first statement here. So if triangle ABC is isosceles, so that phrase follows the word if, so that is P. Then it has two congruent sides. It has two congruent sides is Q if we use our same format as above, if P, then Q. So that is a true statement. So we've met our first requirement to use the law of detachment. Now we have to have a given. What this will look like is a sentence, some sort of statement. Okay, no if, no then, no question mark, just a statement. Triangle ABC is isosceles. So the first thing we have to ask ourselves is, well, does that satisfy the condition for P to be true? Well, P says triangle ABC is isosceles, and that is exactly what our given says. So yes, P is true. So my conclusion is therefore triangle ABC, because we don't want to say it. Your English teacher would say, what's it? So use your noun here instead of just it has two congruent sides. So triangle ABC has two congruent sides. Let's try this one more time. So we're going to use our conditional statement. We're going to find P, that's the hypothesis. In this case, an angle has a measure greater than 90 degrees, and that is P. The conclusion in that conditional statement is it is obtuse. So that is Q using our format from above. All right, and then our given is that the measure of angle A equals 98 degrees. Well, this doesn't match word for word what P says, but if the measure of angle A equals 98 degrees, then that is a measure greater than 90 degrees because 98 will always be greater than 90. So, P is true. So we have now satisfied all our requirements to use the law of detachment. So our conclusion is therefore Q. So therefore, all right, we're not going to say it. We're now going to say angle A. That's the noun that it is referring to. Angle A is obtuse. Okay, something else we can do is we can look at an argument. So that is the combination of a conditional statement, a given, and a conclusion. So we have a conditional, we have a statement, and a conclusion here. So we're going to say whether the argument reached is valid. Okay, so whether that conclusion follows using, in this case, the law of detachment. All right, so in our conditional, the hypothesis is x is greater than 12. So that is P. The conclusion is x plus 9 is greater than 21. So that is Q. My given is the value of x is 14. So we have a true conditional statement. First check. All right. Now we have to see, is P true? Well, x is 14, which is greater than 12. So P is true. Now, the conclusion should be therefore Q. So the question is, does this statement match Q? X plus 9 is greater than 21. It does, so we say that this argument is valid. For B, we're going to go through the same process. We're going to identify the hypothesis of my conditional. Two angles form a linear pair. The conclusion is that they are supplementary angles. My given is that angles A and B are supplementary. Now, while supplementary angles are named in the conditional statement, it's in the conclusion, not in the hypothesis. So it is not in P, instead that's in Q. So I have not met the requirements to use the law of detachment. It must be the hypothesis that is true, not the conclusion. So I don't have the requirements to use this law, so I can't draw any valid conclusion. It may still be a correct statement, maybe in some cases, maybe in all, but based on this law, it's not a valid conclusion, so we say that is invalid. Our second law of logic that we are going to look at is the law of syllogism. So the law of detachment only had one conditional statement. The law of syllogism, all right, allows us to take two true conditional statements, all right, and we can create a single conditional statement as long as the conclusion of one, so Q, is the hypothesis of the other. So then my next conditional statement must have Q as the hypothesis if it's the conclusion in the first one. Now, I don't necessarily have to write them in either order. So the example for this is if I'm a teacher teaching driver's ed, then I can tell one group of students, all right, if you want to stop the car, you need to hit the brakes. All right? Now, when might you want to stop the car? Well, if a light is red, that means you have to stop. So the law of syllogism says I can link those two statements together, which is why this is also known as the chain rule. Although on the quiz or test, you'd better put law of syllogism. All right, but I can link those two statements. So, if the light is red, I need to stop. And if I want to stop, then I need to press the brakes. So I can link those by essentially taking Q out of the middle. And so Q here is needing to stop. And so the new conditional statement is, therefore, if the light is red, then I need to hit the brakes. All right, let's use this in a math scenario. All right, we're going to identify the hypothesis in our first conditional statement. X is the midpoint of segment YZ. The conclusion to that one is that the measure of YX equals the measure of XZ. All right, and then the next conditional says the measures of two segments are equal. Well, that's the general case of what we just said here. So even though the first one was talking about two specific segments, this is still an equivalent statement in logic. Okay, we just have a specific and a general case. All right, and now we have a third different part. Okay, they are congruent. So now I do have measures of segments being equal in both parts. So based on this setup here, okay, Q is going to be the portion that is in both. Okay. In the statement where Q is the conclusion, all right, the first part of that, the hypothesis of that same statement, is going to be P, and the conclusion of the other one is going to be R. Okay, and we can use our law of syllogism to say that our conclusion must be, therefore, if P then R. So in this case, that is if X is the midpoint of segment YZ, then R. They are congruent. Well, in this case, there hasn't been anything in this sentence that they would refer to. So in this case, they are the two segments listed, okay, for the measures in the Q of the first one. So they becomes segment YX and segment XZ, okay, is now they, because we're not talking about the measures, we're talking about the segments themselves. So they are congruent. All right, next one. We're going to identify the parts of each of these conditionals. So here I have a hypothesis and a conclusion, and then X is greater than 5 does not appear in the first conditional, so it gets a different color, all right? But X squared is greater than 25, I have seen before, all right? So I have two true conditional statements, all right? And this conclusion here is then the hypothesis here, so I do meet the requirements to use the law of syllogism, even though these sentences are not written if P then Q, if Q then R. They're written the other way, if Q then R, and then if P then Q. It doesn't matter what order we say the conditional statements. What matters is the order of P then R in my conclusion here, okay? So, I know using the law of syllogism that my conclusion is, therefore, if P, so X is greater than 5, then R, X squared is greater than 20. In our next two examples, we're going to state whether each argument is valid by the law of syllogism. Not necessarily a valid conclusion, but whether we use the law correctly. So, hypothesis, conclusion, that same statement shows up again, all right, that angle A is acute, and so then this last one is a third color. So I'm going to label these. Q is the one that appears in both, so angle A being acute is Q, all right, P is the hypothesis when Q is the conclusion, and R is the conclusion when Q is the hypothesis. Right? So based on the law of syllogism, our conclusion should be, therefore, if P, then R. And those indeed do match, so this is valid. Okay, B. If a number is divisible by 4, then it is divisible by 2. If a number is even, that's a third statement, okay? And then a number divisible by 2, we used red there. So, in this case, divisible by 2 appears in both of my conditional statements. However, it's the conclusion in both. So, according to the law of syllogism, I can use this when the same statement is the conclusion in one and the hypothesis in the other. That condition is not met, so I cannot use the law of syllogism. So even though that last statement, the conclusion, if a number is divisible by 4, then it is even, is actually a true sentence, it is not a valid argument by the law of syllogism in this case. Okay, so this one is invalid. Using these two laws of logic, we can combine them to draw a conclusion from some given information. So if I have two conditional statements, I'm going to use the law of syllogism first, and I'm going to use that to make one new true conditional statement. And then once I have one true conditional statement, if I am given that the hypothesis to that one is true, then I can use the law of detachment to make a final conclusion. All right, so let's try that. All right, example A, if 2y equals 4, then z equals -1. Okay, so I have a hypothesis and a conclusion. Another statement, so I'm probably going to be looking at the law of syllogism here. If x plus 3 equals 12, that's new, so a new color. Then 2y equals 4, which I've seen before. Okay, so that statement, 2y equals 4, is in both conditionals, so that becomes Q. All right, x plus 3 equals 12 is the hypothesis when Q is the conclusion, so that makes it P. And then z equals -1 is R. All right, so we've met all of our conditions to use the law of syllogism. So therefore, we can write a new conditional if P, if x plus 3 equals 12, then R, then z equals -1. You notice we haven't looked at that last statement in my question, in my example at all yet. Once I have a new conditional statement, now we can go look at this. All right, there's no question mark, no if, no then. That is just a given. So given P, all right, now I know that I can use the law of detachment because I now have a new P, and although this is R from our original one, you could think of this as a Q prime, okay? So I know the hypothesis is true, so the conclusion must be true of that conditional. So I can say that z equals -1. Okay, moving on. Last one. So if two angles form a linear pair, then they are adjacent. If two angles are adjacent, then they share a common side. So here, Q is two angles being adjacent. P is that those angles are a linear pair, and R is that they share a common side. Q is indeed the conclusion to one conditional and the hypothesis to the other, so we can use our law of syllogism, and we're going to combine them to make, therefore, P if P then R. Sorry. So if P, if two angles form a linear pair, then R, they share a common side. So we now have a new single conditional statement that is true. Okay, and now we're going to go look at our given. Angle 1 and angle 2 form a linear pair, which is indeed the hypothesis of my new conditional. So I know that the conclusion to that must be true. So, therefore, angle 1 and angle 2, because I have to say what they refers to, okay, but they share a common side.